So now we're going to talk about a type of reaction that we've not talked about before, and this is called an oxidation-reduction reaction. Okay, and so oxidation-reduction reactions. These are called redox for short. And what we're really talking about or really thinking about, and this is the first time that we're really going to do that, is we're going to talk about a reaction, or this is a reaction, in which electrons are transferred from one reactant to another. Now, make no mistake, electrons are transferred in reactions all the time. It happens more often than it doesn't, to be completely honest, but this will be the first time that we've ever talked about it this way. Okay? And that's all right. It's just where we're starting, where this is our entry point into this. Okay? So, corrosion of metal is the most common place where reaction happens. So this is the most common redox reaction type. And so this is where we're going to start. Now, when this happens, each atom of the metal loses an electron, or more, because they can give away more than one electron, to form a cation. And when that happens, that cation then can go and react with anions around it. With the other anions around it. Okay. Now, the easiest way to think about this and to remember this is that losing electrons is oxidation. So when your car starts rusting and turning into a rusty heap, which is happening to mine again, unfortunately, that brown color is what's left of iron. That is iron losing electrons and turning into iron 2 oxide. And so that's an oxidation reaction. That's what's happening. Okay, so if we were to talk about this in specific reactions or a specific reaction, we could say that we would have calcium as a solid plus oxygen. I'm going to leave it as O2 in a gas phase. We could take that and we would see that it was making calcium oxide. And in this case, it would be a solid. Okay. If we're going to balance it out, we put a 2 here, we put a 2 here, and that would be happy news. And so what's happening here is calcium is being oxidized to Ca2+. And then when that reaction happens, then O2 is turning to O with a 2- charge. And so that's how the chemical reaction is happening, and that's what's going on in that particular example. Okay? Now, so this is being oxidized. If one thing is being oxidized, the other piece has to be being reduced. And so in this case, oxygen is being reduced, or becoming more negative. So something that is being reduced is becoming more negative in charge. Something that is being oxidized is becoming more positive in charge. And so the calcium is turning into Ca2+. Now, gaining, so losing electrons, we already said, and I erased it, but losing electrons is oxidation. Gaining electrons is reduction. Okay? So gaining electrons is reduction. And that's kind of backwards, but you just got to kind of play it into your head, okay? Two ways to remember that, okay? Leo says Gur. Okay, losing electrons is oxidation. Leo the lion says Gur. Gaining electrons is reduction. So Leo the lion says Gur. The other one that I remember is oil rig. Okay. Oxidation is loss of electrons. Reduction is gaining electrons. So that's how I remember oxidation versus reduction and how this is happening and what we're going to be talking about that way. So that's how I play that one out, and that's how I remember what's going on. So now what does that look like in a chemical reaction? And so let's talk about oxidation of metals. And so first one we're going to talk about is by a single replacement reactions, okay? So if I have solid magnesium, to it we're going to add hydrochloric acid. This will be aqueous. We're going to make MgCl2, and this will be aqueous, and it's going to make H2 gas. Okay, so am I balanced? One magnesium, two H's, two chlorines, two chlorines. Yep, we're balanced. All right, now, in order to understand and how to do this, we have to be able to track how many electrons something has. Okay, there are some rules for that. We're going to go through that shortly. But I'll just tell you, these are called oxidation numbers. Okay, and oxidation numbers or oxidation states. All right, and so it's kind of an arbitrary electron counting scheme. And that's what we're going to use to do this. Okay, so the first thing that I want to tell you is that the oxidation numbers of elements as they appear on the periodic table and in the state that they are on in the periodic table means that they have an oxidation number of 0. Okay, so my oxidation number for magnesium is a 0. Okay, my oxidation number for hydrogen gas, because hydrogen lives as a gas and it is what it is going to also be a 0. And so I'm going to put a 0 over here. All right. Now, I'm going to tell you what the oxidation numbers are in this case because I want you to know. But for now, okay, we're not going to worry about it too awful much. So hydrogen in this compound has an oxidation number of a +1. Okay. The oxidation number of magnesium over here is a +2. That's the same as its charge. We're going to talk about that in just a little bit. And then just out of habit here, we're going to write the oxidation number of the chlorine as well. That's a -1. That's a -1. Okay. Now, let's talk about how this changes and what doesn't change. All right. So let's look at magnesium, and we're going to tie it all the way over to there. Okay. Now, each individual magnesium goes from a 0 charge to a +2 charge. Now, what charge do electrons have? That's the question you have to ask yourself to be able to do this. So electrons have a -1 charge. So to gain a +2 charge, this magnesium atom has to have given off 2 electrons. Now, if you look at the electronic structure of magnesium, you know that it has 2 electrons in an s orbital because it's a group 2 metal. It's the second one over on the periodic table. And so that's the other reason that we know what's going on. But magnesium has lost 2 electrons. Okay? And so this is oxidation. Remember, the other line says Gur. So losing electrons is oxidation. Okay? Now, let's do our tie line here with our hydrogen. So hydrogen goes over to here. Now each hydrogen atom has added or gained one electron. So each atom gained one electron, and that's reduction. Gaining electrons is reduction. Okay? Now, so each hydrogen atom, there's 2 hydrogen atoms, so I'm going to write 2E minus total. Okay? I'm going to go back to here. 1 magnesium atom, 2 electrons, 2 electrons total. Okay, do we care about this? Well, the number of electrons that something gives up has to equal the number of electrons that something can take in on the other side. Okay? And so we have to make sure that the number of electrons given equals the number of electrons received, and those electrons have to be transferred during the course of this chemical reaction. Okay? So that's the big thing that we want to think about here. So, and that's going to be a key learning here, is that the number of electrons... No, my marker is squeaky and dying. No! The number of electrons transferred must be the same, or we've done something wrong. Okay? So the number of electrons gained has to equal the number of electrons lost. Okay? So we're going to work our way through what that means, and we're going to talk about how that works in just a second. But for right now, that's how that's going to go. So, all right. So one of the ways that we have to figure out how this works is using something that we call the activity series. Now, I started this video the wrong way to bring a file in, so you're going to have to bear with me, all right? Now, you guys used activity series before to predict products in a single replacement reaction to see if it was going to happen. Now, I gave you a simplified version of the activity series previously. Now we're going to talk about it so that it's got another component in it as well, all right? And so this one, I'm just going to draw a couple of them from the line just to show you what they look like so you can see what it talks about here. But if I talk about lithium as a solid, and I show an arrow where that chemically reacts to make lithium plus aqueous plus an electron. Okay, so no charge, plus 1 charge, 1 electron. And that's really all I'm trying to show is the number of electrons that get transferred. Now, that number of electrons that gets transferred is the same thing as its main charge that you see off your periodic table, because that's the number of electrons in its outer valence shell. Okay, aluminum. So aluminum as a solid is going to go to Al with a 3 plus charge, and it's going to give up 3 electrons. Okay, so that's the activity series, and we remember how to use this, but more importantly, what I want you to remember here is that any metal can be oxidized any metal can be oxidized by any metal below it on the activity series list. Okay, and so that's another reason that we want to look at the activity series, is to see how many electrons can be transferred and to see who is going to be able to make sure that that transference or that oxidation can occur. So that's what that is. And so assigning oxidation states. this is going to be a big slide. There's going to be a lot of work here. Okay, and then we'll come in and we'll work through how to do this actually. So make sure you get it in your notes and we'll actually walk through it and see how it goes. Now, oxidation states is a bookkeeping method. Okay. That's funny. Okay. I think it does actually have two Ks. I think it really does. Bookkeeping, yeah. It doesn't look right to me, but whatever. Oxidation states are just a bookkeeping system. That's all it is. Somebody made it up and said, okay, it's a bookkeeping system. We're going to track electrons with it. And so that's what we're doing, all right? So, the rules. There's going to be several rules here, and I'm going to do what I can to try and simplify them for you, but we'll do what happens, okay? So the first rule, number one, for an atom in its elemental form, its oxidation number is 0. Okay, so H2 is a 0. That's how it is in nature. So each atom has an oxidation number of a 0. So too with F2, Cl2, Br2. Solid aluminum, Al is a solid, oxidation number equals 0. So the state it's in on the periodic table, when you see it, that is its oxidation state. It's 0. Okay? Okay, number 2. Any monoatomic ion the oxidation state is the same as its charge. Okay, so if I have a +1 charge on a hydrogen atom in a compound, its oxidation number is a +1 or a 1+. Okay? So that's how that's going to roll into this as we work through it. Okay, so a potassium plus 1 ion, its oxidation state is a +1. Okay, a sulfur that has a 2- charge, its oxidation state is a +2. Okay, alrighty. Rule number 3. Nonmetals. Usually negative, they can be positive. So more often than not, they are usually negative in charge, but they can be positive. And that makes sense if you look at all the different charges that are on your periodic table, or the oxidation states that are possible for nonmetals. So it's on the right-hand side of the stair step. It's that spot, it's that place, that's where we see all those different charges, okay? So we're going to break these down by element. So oxygen is usually a -2 oxidation state, okay, in both ionic and molecular compounds. Exceptions are peroxides. In which oxygen looks like this, O2 with a -2 charge. And in its case, its oxidation number is a -1. Okay. So that's oxygen. We're going to call this point A. Point B, hydrogen, is usually a +1 when bonded to nonmetals. And hydrogen is usually a -1 when bonded to metals. Okay, so it depends on who it's hanging out with. Hydrogen can be duplicitous in its nature, and if it has to, it'll give up an electron or it'll take an electron in based on who it's with. Okay, so that's hydrogen. And then the last one here, I'm going to pause it so you don't have to see me erase it. Yeah, so and then I'll just write 3B and go from there. Okay, so we're still 3. We just did B, we're going to do 3C. Okay, so this is fluorine. Fluorine is -1 in its oxidation states in all compounds. Okay, so fluorine is a -1 all the time. The other halogens, that's everybody underneath fluorine. The other halogens usually are usually -1 in their compounds. However, when they are combined with oxygen, they form positive oxidation states. So, unless combined with oxygen. And in that case, they will have positive oxidation values. Okay? And then rule number 4, and this is the important one here. And so really what we're looking for is these are like guidelines to add them up, figure out how much they are, so we can figure out how much electrons are transferring away from somebody. Okay? So the sum of all oxidation numbers for all atoms in a neutral compound equals 0. Okay. Similarly, the sum of oxidation numbers for all atoms equals no, for all atoms equals the charge on the ion. Okay, so if I have, I don't know, HCO3 with a -1 charge, so that means then that the charge, the sum of all the oxidation numbers for that has to equal a -1. And so that's how we're going to figure this out. And I'll show you what that looks like in class. Okay? So with that, that's what we got. Thanks again, and we'll talk at you later. Bye.